right, so another object that we kind of see in our everyday life, the pendulum also behaves like a simple harmonic oscillator, right? So it's an object that oscillates back and forth, has periodic motion that's consistent over time. Why does it oscillate? Well, it has that restoring force. If I pull a pendulum back, there's a bob on a string, and I pull it back, the restoring force of gravity pulls it back to that center point, where then continues on because of its energy to the other side and exhibits that behavior. So like the simple harmonic oscillators we've described in the previous introductory video, so I encourage you to go certainly look at those to get some of that background, we can also use that information for a simple harmonic oscillator of a pendulum. Now it's important to make a note, however, that this model works if our angles are small, all right? And the math is shown, I'm sure, in whatever textbook you use, or if you use an online resource, that math is shown for you. We're not going to talk about that here. We're just going to do the conceptual idea and then utilize that information. But it's important to recognize that this is if we have angles that are no greater than 10 degrees. Okay, so we want to keep them less than 10 degrees. All right, so that's going to be an important thing. So, what do we do with simple harmonic motion? What do we use to describe simple harmonic motion? And from, again, those previous information, we talk about the frequency, so how many cycles the pendulum is making in a certain amount of time, or per second, how many cycles it's making per second, and the period, how long does it take for the pendulum to swing out and back, one complete cycle. So what is that dependent on? Okay, what controls, what influences the frequency or the period, the timing of the simple harmonic oscillator? Well, we learned when we first introduced the mathematics of simple harmonic oscillations in the spring, we learned that restoring force was important. Gravity is going to be the thing that's pulling that pendulum into that motion and that periodic behavior. So gravity must play a role. If I were going to go to another planet where the gravity was slightly smaller, or if I'm a very keen clockmaker and I want my clocks to run just as good at sea level as they do up at Pikes Peak, then I need to be paying attention to the actual gravity values because that's what's causing that restoring force. All right, so gravity plays a role. How might gravity play a role? Well, if I increase the gravity, I have a stronger pull down. Increasing the gravity is going to make that periodic motion go faster. So if I increase the gravity, I increase the frequency, I decrease the period, okay? And of course, the reverse, the increasing frequency and decreasing period is because of that inverse relationship. All right, so gravity plays a role. What else might play a role? I want you to think back to when you were a little person and you were swinging on swings at the park. If you can remember, what influenced sort of your experience with swings on the park, whether you went really fast, high frequency, or really slow, low frequency. If you think back, and if we actually look at the math, it has to do with the restoring force, but the length of the string that the swing was on played a role. So length also matters in our timing of the simple harmonic motion. If I increase the length, really long swings, they went really what felt like slow in terms of the cycle. I decrease the frequency, and of course then the time it takes to do one cycle increases that period. And if we do the math, we'll discover that the frequency of a pendulum, a simple harmonic motion of the pendulum, is very similar in looks as it was with our spring. The frequency is given by 1 over 2 pi times the square root of g over the length. And our period then, of course, is the inverse of that. So it is 2 pi, the square root of the length, over our acceleration due to gravity. Now notice what's not in there. the mass isn't in there. Okay, so how heavy the person is sitting on that swing doesn't influence its period. My little brother had just as long of a period on the swing at the park as I did on the swing on the park. So mass isn't included in there. And the other thing is the amplitude. Again, low amplitude. But the other thing is the amplitude, very similar to what we saw when we looked at a spring and simple harmonic motion on a spring. Now, if we're in these small angles, we can actually use that equation of motion. We can look at that cosine wave, but we talk about it in terms of the angle that the pendulum is making. And so the angle as a function of time is equal to the max angle times the cosine of the angular frequency times that phase. And again, we're not going to utilize that phase in our studies, but it is important to recognize that can be a part of the motion itself. All right, so let's use these newfound equations to solve a problem of a pendulum. So let's imagine that you're an engineer for the city planner, and they want to put in a new park. And they're really thinking about the caregivers that take their young children to the park. And so they're thinking, we want to put a swing there that allows the caregivers to have a conversation while they're pushing their children on a swing. So we think that we want them to only have to push once every 3 seconds. If we have a 3-second break where we had to pay attention, we can probably carry on a pretty good conversation. Throw 3 seconds for every push of this swing at the park. And the city planner wants to know if that's reasonable. Can I make a swing? Can we construct a swing set that allows caregivers to only have to push once every 3 seconds? All right. So basically, we got to determine how long is the string. We're going to have a push. That child is going to be in periodic motion, simple harmonic motion. Every 3 seconds, the parent's going to push. So every 3 seconds, they're going to come back to where that caregiver is standing. So they start at the caregiver, they go out, they come back to their start point. That's a cycle. So this gives us our period of that motion. So if we describe what that period means, the time per cycle, and I imagine pushing my child out and coming back and pushing my child again, then I complete one cycle before that second push. So our period is 3 seconds. So given that information, how long do we have to make the string? Well, we just learned that the period is equal to 2 pi times the square root of L over G. And we're going to use 9.8 as our gravity, sort of that standard in our part of the world. So 2 pi times the square root of L over 9.8 is equal to 3.0. So I'm going to divide both sides by 2 pi. So I have 3.0 divided by 2 pi is equal to the square root of L over 9.8. Square both sides. Make sure I'm not getting too low. 3.0 times 2 pi squared is equal to L over 9.8. And of course, then multiply it by 9.8. So I have 9.8 times 3 over 2 pi quantity squared is going to give me my length. So 3 divided by 2 pi squared times 9.8. And we have a length of 2.23 meters swing. Perfectly reasonable length to make a swing on a playground. All right, so recognizing that a simple pendulum is a simple harmonic oscillator. We talked a little bit about what influences the period and the frequency of that oscillation, and then using that relationship to solve a problem. Good job.